All right, what if the question says, start with this ketone and create this product via the stork enamine synthesis. And if you remember back from our discussion, the nitro group is essentially the same thing as a carbonyl in terms of its electron withdrawing ability, its ability to stabilize negative charge. And so you can see that I've added 2 carbons and an electron withdrawing group. And basically I have a 1, 2, 3, 4, 5, 1 to 5 relationship between the original carbonyl and the new electron withdrawing group. It could be a carbonyl. So I could also have proposed this product. It's really going to give us the same answer. I'm going to start with the nitro group though. So if I wanted to start with this ketone, that means I have to make this bond right here. That means I might want a double bond here and my nitro group. So this is going to be a vinyl nitro species. And because this is an unstabilized enolate, the first thing I want to do probably is to create the enamine, which will react better in this Michael addition. So my product, the intermediate in this case, would look like this. My new bond, this is the first carbon, the second carbon of the vinyl group. Here's the nitro group as it is absorbing the negative charge temporarily. And then mild acid workup will not only protonate the nitro group at this position, allowing us to reform what we are used to seeing as the nitro group, so we'll protonate it right here. It will also hydrolyze this iminium cation back to the carbonyl. And I could have made this species here. Let me outline that in green. I could have made that species had I used that unsaturated aldehyde. Basically, it's the same procedure, just that I would have had a different electrophile in this case. Let's look at one more example before we move on. What if I am directed to use this ketone to make this species via the stork enamine? Again, I can look at this as my nucleophile. Either of these alpha carbons can create an unstabilized or a not very stabilized enolate. So this is not a good candidate to simply deprotonate to the alpha carbon. I'm going to make this bond right here, and we can see that I'm set up to create an alpha beta unsaturated ketone as my electrophile here. So let's go ahead, make the enamine. I have to recognize that this would create a not very reactive enolate. And I'm going to react that with this. So I recognize that this should be the shape of my electrophile. And if I'm making a bond at the beta carbon, then I need to have in my starting material a pi bond right there. And so that's why you see what I've drawn right here. And again, that's going to, actually, let's count carbons again. Just so I don't lose any. I'm going to create a bond between carbons 2 and carbon 5. I'm going to create a new pi bond between 6 and 7. I'm going to push electrons onto the oxygen. There's my new bond to 5. Really doesn't matter how I draw this as long as I keep track of all my carbons. So let's go ahead and number them again. 1, 2, 3, and 5, 6, 7. This one's 4, although we found that 4 is really not necessary, or at least the numbering is not necessary. I'm going to have a new pi bond between 6 and 7, and my oxygen is attached to 7. It is now a negative. And with H3O+, again, this enolate gets hydrolyzed. This enamine or iminium cation also gets hydrolyzed to reform the carbonyl here, and really just rotation around carbons, the bond between carbons 1 and 2 will give me this orientation for the product. So my product here is not any different, it's just slightly rotated compared to what we had as our desired product. One last thing to consider in this section is what's called a Robinson annulation. It's another way to form rings, basically. So let's look at a stabilized donor for a Michael reaction, and let's look at methyl vinyl ketone. So this is going to be the donor, this is the acceptor, and you'll notice I'm starting with a more stabilized Michael addition, or Michael donor. This doubly alpha hydrogen here can be removed, makes a stabilized enolate that can participate well in Michael reactions. So I'm going to react that with NaOH, and as we might expect, the anion that's formed right here is going to react with the beta position on the methyl vinyl ketone. So let's draw that intermediate first and see where we get. So I need to have 1, 2, 3 for my carbonyl, and then the methyl. So I'm adding 4 carbons, and I've had 1, 2, 3 carbons already, so I need to add 1 more and make sure that the carbonyl is right there. So that's the first intermediate, or that's the intermediate. But remember, we're basically mixing these together in a pot with sodium hydroxide present, and we're probably going to use heat. There's really no way for us to say, I want you to stop here and not do any more reactions if that is a possibility. And really, it is a possibility. Now that we have all these carbonyls, we still have alpha carbons. We've got sodium hydroxide, and if you look at the methyl group that's hanging off here, if we count 1, 2, 3, 4, 5, 6, if this methyl group attacks this carbonyl or even this carbonyl as sort of an aldol reaction or aldol condensation, we might be able to form a ring. And there's really no reason that the sodium hydroxide and heat would stop and not react with this. So let's go ahead and do that. We're going to make a ring, and I will number these again so you can keep track. I'm going to deprotonate carbon 1, and I'm going to attack carbon 6. So some more NaOH. This would be an aldol condensation. And I'm going to make, let's see here, I need to number this so I can keep track of things. I know 5 is the spiro atom here, meaning it's the atom that's going to be part of both rings. And then 4, 3, 2 is where my ketone is, 1, and 1 made a bond with 6. And I know that 6 has a methyl attached to it. I know that 2 is going to have the ketone still there. And I should have a double bond between 1 and 6 because that is what the aldol condensation does. I make a double bond between the nucleophilic carbon of one of the carbonyl species and the carbonyl carbon of another carbonyl species. And so you can draw the aldol mechanism here, just like we drew earlier this chapter. And you can draw the Michael addition mechanism here, just like we drew earlier this chapter. So this is no new mechanisms, just that we're combining 2 together. And so we make this species. You can see that my carbonyl used to be here at number 6. Number 1 used to be a methyl group. Now it is a double bond to carbon 6. And a few interesting points about this. We can do conjugate addition reactions with this product. Also, do the Michael reaction first. That's what we should always do when faced with a Robinson annulation type setup. So let's just look at one more example. What if we wanted to use just a simpler dicarbonyl species, and ethyl vinyl ketone. So the first step would be to take this doubly alpha hydrogen, react it with the beta carbon. 1, 2, 3. And so I've made a new bond between this carbon and this carbon. That is right here. So you can see that there are 5 carbons here. That comes from my ethyl vinyl ketone. And then again, let's do some numbering. So you can see that there's now, if I were going to use this methyl group, there are 7 atoms between it and the next carbonyl species. So a 7-membered ring is rather unusual. Typically the Robinson annulation ends up with 6-membered rings. So if I use carbon 2 as my nucleophile, carbon 7 as my electrophile, I should be able to get a 6-membered ring. So let's just see if I've added those correctly. It is quite possible that I left a carbon out. That's why I'm going to number everything. 6, of course, is the branch point right here where I've added that new bond. And then 5 is the first carbon of the ethyl vinyl ketone. So I'm not sure. Nope, I'm numbering that totally wrong. All right, so I have 6 atoms in my ring. Actually, I have 7 atoms in the ring, so that means I need to fix it. So you can do this whenever you're answering a question too. And that means I need a methyl group on carbon number 2. There we go. So there are my carbons. You can see how I've troubleshooted my product answer and discovered that I had extra carbon in my product. And you can leave this drawing just like this. That's totally fine. It doesn't have to look super pretty. You can redraw it if you wish. But basically what we're doing here is we're reacting carbon 2 as a nucleophile with carbon 7 in an aldol addition reaction. Or I'm sorry, an aldol condensation. And yes, this is a long mechanism, but you've seen both pieces. It's just a matter of putting them together. NaOH with heat performs the aldol condensation. And then, just to make sure all of the NaOH is gone, mild acid workup gets us to this product.